Continuing on with Class 21, which is covering dynamic force analysis and mechanisms, we're going to go to the next section here where we take the force analysis of a 3-bar crank slide linkage. This is a little bit of a weird looking one. I'm not sure why he's making these triangular shape pieces. I think it's mostly to try to get the center of gravity over to the away from the where the linkages are. All right, so that we have these different joints, and they want to move the center of gravity far away from the thing. So it looks like kind of like sort of a big thigh or something. I'm not sure. Anyway, and there's also, oddly enough, there are these traveling forces that are attached to the pieces. Now we want to take something like this and break it down into its pieces. So this is the ground over here, and it's not really a free body diagram because it's not free, right? But they're the grounds. But those are going to be the reaction forces. These are going to be the forces that they're opposite the reaction forces. But we have, for instance, this F12 compared to the F21, and they are equal and opposite in direction. We also have position vectors that we want to try to look at from the local non-rotating coordinate system. So that local non-rotating coordinate system is this X and this Y for this linkage. And we also are going to have some kind of force that's placed right onto here. We're going to have a force at each joint, right? And some of these are going to be reaction forces, but also they're going to, in this case, because there's multiple linkages, they're going to be applied forces, right? So this right here is sort of a reaction force, but over here it's sort of an applied force. It's like for this link number 3, this force F2 onto 3, so you can always think of those numbering that way. This is the force of link 2 operating on link 3. That could be like, you could think of that for here as an applied force. Now we have 2 coordinate systems because this piece is both translating and rotating. We have a translational coordinate system. So this is the local non-rotating coordinate system. And we also have a moving coordinate system right here. That's going to be at this joint right here. And so we have the local rotating coordinate system. And so that's sort of the key to trying to find out the pluses and the minuses and to navigate through them. Norton gives us these accelerations for things. Like there's an acceleration right there, and there's an acceleration right there at the center of gravity. But we can find those ourselves from the previous sections of the book. So I don't know why he doesn't also include those. I guess he was just saying, well, you can get them yourself, so he won't do that. And now we have that strange, I think I've already mentioned it, that strange external load for no apparent reason that you were like, well, how did that load get right there? So, well, I guess he's doing a what if. What if there was that load right there? But I'm not sure how you get a load to always be there. It's kind of weird. I think I actually forgot to mention that I forgot to mention a couple of SolidWorks things in the previous video, so I'm not going to go back and record it, but I'll try to mention it here. Something else I probably forgot to do is that this thing is being motivated by this torque. That's the torque that's getting this thing, this weird looking mechanism to move, and it's going up and down in this slot right there, right? So there's not a piston necessarily. So we kind of call it a 3-bar kind of crank slide linkage. It doesn't have a piston. Piston doesn't have any mass. But what it does is it's got something that's kind of like friction, except it changes directions. The direction of the friction changes direction each time. And if you start to think about it, well, that would make sense, right? It's always going to be resisting the motion, and so it's going up and stopping and then coming back down. That creates sort of a little dilemma when trying to calculate things with a computer, but not too much. It's somewhat nonlinear. It's not quite intuitive. So here is the basics. I should also point out that this is in the book, so you can. I'm really just being your tour guide and trying to help you get through this and understand it better, instead of just giving you the big picture. By the way, this right here, this little that guy right there, is that sort of like their symbol for it being a changing sign each time. So you could think of this as the normal force, and you can think of this as the friction force right there. And the normal force is changing values as you go along, and you can see this absolute value because it could be either pushing from one side or pushing from another side, and it doesn't really matter whether it's positive or negative. It doesn't influence the value of the friction. So I'll walk through this other part of it right there, even though it's right there in the book for you to read yourself. And sometimes this thing will not let me pick that. Okay, so here are the forces that are being applied to link 2. This is that guy right here. And also, by the way, we're also including the mass times gravity and mass times gravity. And over here, we're including the rotational mass moment inertia times the angular acceleration. You should also note that when we go to solve things, because we were going to be, these right here are, let's say this the wrong way. We'll see how we assemble that, right? So we place all of those together and also include this friction, and this is a good, like a Coulomb damping type of thing. Sometimes people call it stiction. It's kind of interesting, right? It depends on which direction the velocity is going to be. Like, if the velocity is going in this direction, it's a positive. If the velocities, if velocities come in this way, this is also negative, right? So they kind of like agree with each other, all dependent on the direction of the velocity. We're going to arrange these matrices with unknowns in a column on the left-hand side and the knowns on the right-hand side. So one of the things, I messed up when I was saying some of this. This piece right there, these are known forces, so they end up coming onto the other side right there. So that's why we have these right here. And this is that FP, that weird, that odd duck thing coming right up in there. But we had links 2 and links 3, so we systematically put them together and arrange them. So here are the unknowns, and we have the X and Y components at each of the joints, and we have the applied torque. So here's the example 11.2, and where we have used, it's going to be in 60, this crank is going to be at 60 degrees, starting out with 60 degrees. It's traveling at 30 radians per second, and it's slowing down at a rate of -10. And then they've given us the acceleration of this spot right here, G2. And they've also told us, so they've done a position analysis right there, right? That would be a necessary thing where, we did back in chapter 4, right? We did position analysis. Well, that's done for us in this. Also in chapter 6, we did the angular velocity analysis. Chapter 7, we did the angular acceleration analysis, right? And we could use all of those to find this ourselves. So everything on this line right here is something we could find from our previous work. And so there's also this external force being applied right here for whatever reason at -45 degrees. And they don't quite tell us if that's always going to be that is, so 45 degrees. So it follows along. That's with respect to the local coordinate system, which is, you're not quite seeing it labeled there, but you kind of saw it labeled right here, right? So there was the local coordinate system, and you could see that it was that one was measured counterclockwise from that x prime in that local coordinate system. And so it also shows you where the P is located. This is going to be the position vector right here at 2.7 and 101. That's going to be this right there. And that is also measured from the embedded rotating coordinate system right here. And then they also tell you the coefficient of friction. So here's using Bob's stuff with a blob. And here's another one with a blob. I think all right, so here up above, he actually said he had a 0.1 pound inch per second squared. Oh, that's just the mass right there. Okay, I guess because he didn't give the mass. Is that right? Yeah, he didn't tell us the blobs. And then here's all the position vectors and their components. So something that you're going to need to break down first if you want to apply some of these is all this. But, of course, we do it all in MATLAB already, so you have it written, but that's why it's there. And then you do an acceleration analysis, which is a Chapter 7 thing. And then you break down your external load into this. So with all of that information, we're able to create these three matrices, right? The one in the middle here is the one that's the thing we're going to try to find. And all of these right here are just populated with what those values would be. Some of them they didn't quite explain where they came from, so that was what I was trying to do on the previous page. But here is this guy, they're known. So all of these things are known except for that column, and we are able to calculate this and get these values out. The one that they didn't tell us here for some reason is this torque, which I think is the most important part, the torque. But here's the reaction forces, and I'm trying to think of what 3-2 is. I guess we have 1-2. Let me go back and take a look at that. We have 1-2, which is that's going to be right down here, right? That's the force of 1 onto 2, so it's the force of that link. And then we have, then we have 2-3, right? Force of 2 onto 3, and then we also have the force of 1 onto 3, which is up here, right? So there's 3 sets of forces we desire. And here are all of them. So right, what should we have? 1, 2, 3, 4, 5. Only 6. That's interesting. I guess where does... All right, so we have one. We only care about the one in the x direction. I guess because it's the one in the y direction is related to the one in the x direction, so it is not an independent. That's why it's not an independent variable. So if you come back up to here, you could see that we don't have a force right there, but we do have. Ooh, this is interesting right here. We haven't. That's interesting. This guy right there. I guess we can find him, right? Okay, so we have this, which is dependent on because we know this. Okay, so that becomes that's not a problem right there. We have let's see when we get down to here and to populate this. Yeah. Here is this one. Here's this one in terms of our, yeah, okay. So this is related to that guy, right? That element right there. It's got a position vector, and it's also got right there. It's also have a factor that's being placed right onto there. All right. So let's see. We get a MATLAB code. Do all the busy work of establishing the different link properties and putting them all into place. And then here's some the external force and breaking that into components. And there's also the coefficient of kinetic friction. So now you want to get all of these things, these position vectors in place. But I should mention that theta 3 is a position analysis. All right, so, and here's all the position vectors once you do your position analysis, because you gotta need to know what that theta 3 is. And we definitely want to make them related to that localized coordinate system, because the localized coordinate system is dependent on that theta 3 as the thing rotates. So you'll see that there's a theta 3, but there's also a theta 3 of the center of gravity onto the piece, and that is found from, where's theta 3? Where do I do that? Where do I establish theta 3 underscore CG? Oh, I know. Okay, so that's actually up here. That's right up there. That's the position, local position, with respect to the localized coordinate system. So when you go to use the actual position, you need to adjust it for the local offset of that piece right there. A lot of position vectors. Now we do a velocity analysis. So instead of giving us the velocity like they did, I decided let's get omega 3 in this. If we have an omega 2, we can find an omega 3. We can also find the velocity of not the piston, but the point that's inside the slot, by way of this piece, so the piston velocity. So from that, and then we also want to do an acceleration analysis from Chapter 7 information. So we find the alpha 3. It's not difficult, just the equation look kind of long right in there. And so you could also get the piston acceleration. We don't really need the piston acceleration in here, but it wouldn't hurt. There's also the joint A acceleration in the x direction, and the reason why we need that is we want to have we want to be able to get the acceleration of the center of gravity. That's not hard to do with the acceleration of the center of gravity at 2, but when it comes to the acceleration at 3, we have to include that acceleration of point A plus it, right? Because every rigid body acceleration can be found from a combination of translation and rotation. So here's the translation reference part, and then here's the rotating part onto the other side of it. And then, of course, you can find the magnitude and get the angles. So we assemble everything we need to know, and I like to make my MATLAB, and when I can, into a matrix-looking thing that can help me keep track of the piece. So here's the matrices of our degrees of freedom, essentially. We have the torsion's going to be on the bottom, or the ones that represent the angle at the excuse me. At the onto the thing. I'm sorry. Going to keep going. All right. So here's C. Here's all the things that we know about the masses times acceleration. So we have all those accelerations. What we really want to find is the torque, and we're able to find that with by taking A and then the \C, which is matrix solutions. So here are all the results. I'm harvesting the results from there 1, 2, 3, 4, 5, and 6. And then I print out, and then I turn them into magnitudes and angles, and then I print them out at the end right there. And so here's the result that we get. And this is my values versus, oops, I can't do my pen anymore. My values versus, here's my values right here, 177 versus theirs, which is 177. So there is some round off error onto there, but we can see that this MATLAB code is verified for our work. Let's take a look at the MATLAB code itself. Right here is we just looked at it line by line by line, and I'm going to double check that. I used Norton's conventions here so I could match up with his results. And if we run it right there, we will see that we get the 177 inch-pounds as part of it, to confirm, so you can believe me that it actually works. And can we get this one? Can we get any of them to work right now? How about we click over on this guy? All right, so I'm going to go Alt-Tab it. Alt-Tab. SolidWorks. Boom. All right, so I can, I want to talk about full rotation here in a bit. So let's go over to this one. All right, so this is what that ugly looking thing looks like. And here is how I approached it to get this to work. Let's see, I don't know why this thing will not, it's not looking at it. I just want to go that way, okay. And so let's see it go. Seeing it weird looking? How would that even work? Anyway, I've constrained it to be up and down, and I'm not sure if I was able to, how I was able to get the friction, or even if I was able to get the friction. It seems to me I should have a part right here and have some kind of contact going on. But you can see that it's slowing down. Well, it had a -10 onto it, so I had to try to figure out a way for this problem to be able to replicate that motion. I don't know how to make this class anymore, make it more interesting than it is, because it's definitely a snooze fest. I'm out of my depth right here. Where to go? All right. So some things I didn't mention. Well, one thing I didn't mention is that I've adapted also my MATLAB codes to be full rotation so that we could use them in that respects as well. The output of this and the results are going to be, well, you could just show the plot of them, right? This motion of the linear acceleration. But here's the torque right there. So there's the torque that we're looking at. And let's see if I go, let me show the plot of the angular displacements. And it's angular displacement and angular velocity. So you can see that the blue lines are the angular displacement. And you can see the angular velocity is slowly going down. Well, that's because it's a constant acceleration. So it would be going at a constant rate of decrease. That makes sense. But we could kind of see how many times it would have to rotate to be able to do this. And as I had previously done, I went through the process of trying to, some of this stuff isn't necessary for us. Right here, we're going to get to the kinematics. We need to end up at 60 degrees going 30 radians per second at -10 radians per second squared. That is equivalent to 286.5 radians per minute. Revolutions per minute, RPM. And that ends up being at 1,719 degrees per second. So I drew like a little triangle right here. This is really hard to try to explain. But this was my thought process in trying to do this, right? So here's a basic kinematic relationship. Here is in radians per second what we're trying to achieve. And so you could kind of see that the initial radians per second that we need is 40 radians per second, or 382 RPM, or 2,292 degrees per second is where we need to start. All right, so now that's the starting velocity, angular velocity that we need to get to achieve I guess I established the time. I said so I decided that's what I wanted to do at 1 second, because we're decreasing in speed. So I have to start off with a speed, and then go down and hit. So like if this was like so I decided this is going to be 1 second, right? And so I said, well, I want this to be 30 and needs to match up with after 1 second right here. I also decided to go with an angle right here and figure out, well, this is 60. So where do I have to start with the angle? And when I get to right here, so that when I get to the spot that I want to measure, it's going to be what I want. I think that's what I was trying to say. All right. So, and here's the slope. So I had to try to think my way through this. So I had here, I started I start at 40 radians per second. I want to end at 30 radians per second, and I know I'm going down at a slope of negative 10 radians per second squared. So here's the number. Here's the number of radians that need to accomplish. And so it's 35 radians, or 5 revolutions, 5.57 revolutions. So 5 revolutions plus this many degrees right there. So that's how I started the thing out. I know that's complicated and hard to understand, hard to follow. You'd have to go through it a couple times yourself before you could really figure out what the initial displacement has to be in order to land in the right spot. Okay, so what I didn't show you last time was how I did the rotary motor. So here you go. We went with data points right here. Okay, so instead, so we went with this right here, and I edited and I created this. And I probably have, I remember how I did that. So it's 2,292 at 0 seconds. And I said I wanted the thing to go for 4 seconds until it stopped right there. I don't think you had to do that to 4 seconds, but that's what I did. You can see down here, I did it to 4 seconds. And so here's where I started my velocity. And so that when I got to like 1 second right there, it will have given me the velocity that I wanted. So you could see by this. And I do the interpolation cubic line. It's a velocity. So you get the idea. I set it up with data points, and I was able to accomplish it. It was not, this took a lot of time to try to figure out how to do. But hopefully you can follow what I did as part of this. And you can see how it's slowing down. And by the way, I also figured out how to put a force onto this, right? So I had to edit that force. Okay, so first off, I did this. I put that guy in there, a force, I applied it onto there. And that force, I think I found an edge. So there was some way. Okay, so there it is, right there. That blue guy, not the red. The blue guy is the force, and I applied it to a point, or did I apply it to an edge? I think I might have applied to an edge, and then I also had a force direction. And so it was I established that maybe with a sketch on top of the piece, and then I put it as a constant force on there, and then I said it was constant, and then I put the force applied onto it. So there's a force placed onto it. I don't know if I did anything with the friction. I don't think I did anything with the friction. I'm not sure how I applied that or if I did at all. I guess maybe how did things turn out? Probably a little bit differently because of that, because of the torque. Because I had no way that I knew of. I could have done this contact thing, but I would have needed another piece, like a ground piece, for it to go in there. Now this is really touchy because that's a lot more calculations for this thing to have to do. But you could put the different materials in, or you could pick in what the coefficient of friction is going to be, but it has to do a contact analysis, which is tough. What you could do is you could make it two separate pieces so they were flat things. You don't want a round thing touching a flat thing and having to do that calculation and every single time step, because it's the round. Nothing that's round is really technically round. It always has some facets kind of on it, and depending on the number of facets, I don't know. This is just conjecture on my part, by the way. I don't know this, but it can be a more complicated scenario. If you export something here. I don't know which one I'm going to export. I guess export this, show plot, and then plot, and then export to a spreadsheet. And hopefully it'll come up in a second or two. Where you at? There must be that. Where'd it go? I have too many things open. All right, so I got to go Alt-Tab. I think my computer's probably about to explode. Oh, I can't get it. Why can't you get it? Closing things. I should start closing more stuff. Maybe it wasn't done. That's why. All right. So we would say that at 1 second, hopefully this thing will match with what we expect. And so we have 171.7. And that's next class. 177.43. So we got pretty darn close to what we expected in terms of torque. I can't say for sure about the other forces, but the torque is the real thing that matters. And if we are able to, in some way, incorporate this example into our project, what you really want to find out is that motor torque. So that is enough videoing for today.